Good morning, good afternoon, good evening for all of the participants that are joining us today for the webinar organized by the EAGE-EAG Technical Community on Geochemistry. It's very nice to have you all here today. My name is Maria Paula Borges from the EAGE, and I'm glad to welcome you today. In order to start our session, targeting and predicting key resources of the energy transition, then we would like to first introduce a bit of our community, to tell you a bit more about what we do and why I'm inviting you to this webinar series. Then we will proceed with the presentation Targeting Key Resources of the Energy Transition, Hydrogen and Helium by Olivier Sissmann from IFPEN. Then we will go with the presentation by Adriana Traby, Predicting Key Elements of the Energy Transition, Basic Modeling for Hydrogen, Helium, and Lithium. Then we will have the questions and answers for our speakers. In this case, then we'll appreciate your support by leaving all your comments and questions in the chat section so that then we can extend them to the speakers after the presentation so that we can better optimize the time. And then we will close the session of today. Let's then talk about a bit the EAGE-EAG Technical Community on Geochemistry. We are a network of members interested in sharing knowledge and developing skills among geoscientists and engineers crossing paths with geochemical applications or interested in pursuing a career in this field. Our community was established in 2021, and we now currently count on more than 350 members from the association. So the idea is that we can offer this space to you all to exchange knowledge, experiences, and to, of course, try to work all together towards the advancement of our field. As its name indicates, EAGE-EAG, the community operates in collaboration with our associated society, the European Association of Geochemistry. This alliance, of course, goes one step further in the sense that we can connect industry, academia, different actors from the field so that we can explore new opportunities, new perspectives in all the fields of organic and inorganic geochemistry. So this is also an opportunity to, of course, extend our networks and to try to reach all of our members all around the world towards a common goal. So that's why cooperation is so important also for our association, and counting on the support of the European Association of Geochemistry is also very valuable for us to keep up with this conversation, the best practices and lessons learned, so that we can all exchange this knowledge and participate in these joint initiatives together will be more enriching for all of our members. The committee of our Technical Community on Geochemistry is made up by a multidisciplinary group of professionals that are working and developing some research in the field. So we have members from France, Australia, Canada, the Netherlands, Norway, Kuwait, Nigeria, Spain. So we have a team also distributed around the world, bringing together the different perspectives of the field in their own regions. So the idea is that we can benefit from this rich pool of experts and, of course, extend you all of the perspectives to our members. So this is the list of our members participating in this committee and are the ones who are leading these great initiatives that we are now glad to present to you all. In this case, webinar series and other different activities. In this case, for example, we usually participate at the EAGE Annual, hosting different sessions, dedicated sessions, workshops, special panel discussions too. We also have educational networking events and collaborations, such as this webinar series in which you are participating today. Then we'll also share with you news, career advice, vacancies, and try to connect you with the latest trends and research in the geochemistry field in the energy sector for the climate change. So we are there to support you if this is of your interest, to, of course, connect you with all of your fellow colleagues that share this same passion for geochemistry. Then this is an invitation, if you're still not part of our community, that you can join us through LinkedIn. In this group, we share all of this information, latest trends, research, news, vacancies, career advice. So you're more than welcome to join us. You just need to scan the QR code in the screen, and of course, you will be more than welcome to be part of our community. Some last announcements. If you are really interested in this topic of hydrogen and energy storage, you are kindly invited to participate in the GET 2024 conference, our 5th Global Energy Transition Conference and Exhibition, featuring 4 very interesting programs, in this case also featuring hydrogen and energy storage, plus other fields in the energy transition like camper capture and storage, geothermal energy, offshore wind. So in case you would like to keep up with this conversation, you're more than invited to join us in Rotterdam, the Netherlands, this coming November. Plus, there are other initiatives like our international meeting on organic geochemistry coming next year from the 7th to the 12th of September in Porto, Portugal. This event is co-organized with the European Association of Organic Geochemistry, the EAOG, and of course it is a biennial event dedicated to exchange knowledge and experiences around organic geochemistry, featuring extensive technical program, for example, talking about biogeochemistry, petroleum and coal geochemistry, soil and wetland geochemistry, nutrients and sustainability, polyenvironments and bioclimates. And then if you're also willing to share your knowledge in this great event, the call for abstracts deadline is February the 2nd, 2025. Okay, that's all that I wanted to share with you all. Thank you very much for joining this exciting webinar. I hope it is fruitful and enriching for you all. And of course, now let's get to our first presentation with Olivier Sissmann. And I'll stop sharing my screen. Olivier, you can now share your screen while I introduce you to our audience.
Thank you very much. I will try to share my screen.
Yes. Well, Olivier shares his screen.
Is that okay?
To tell you. Yes, that's perfect. Now we can see it.
Do you see it? No, wait.
Yes, we can see it perfectly.
Is it moving? Yeah, it's moving. Okay. Thank you very much for extending me this invitation. My name is Olivier Sissmann, and I'm a researcher from IFPEN Énergie Nouvelle. And today I will talk to you about source rocks exploration and drilling in all continental crust, mostly for targeting what has come to be known as geologic hydrogen. I'm myself a research scientist that graduated from the Institut Physique de Paris, IPGP, and I also still teach at IPGP. And mostly I've been at IFPEN for 10 years working on geologic hydrogen generation and consumption and bio and geo-inspired processes. And I mostly use geochemical and mineralogical analysis for preliminary H2 exploration because those are the less expensive techniques for exploration. Of course, then you've got geophysics, but that's a whole other ballgame. You have probably all heard by now, if you're into geoscience, about serpentinization. Serpentinization was understood over 40 years ago when H2 natural seepages were discovered in the late 1970s. It's basically fluid coming out from hydrothermal vents at mid-oceanic ridges, very rich in H2. It was discovered, I believe, on the Galapagos mid-ocean ridge. And basically, serpentinization is a hydration reaction between the olivine in basalts or mantle rocks. It can be pyroxene as well. And as you can see here, the mineral reacts with H2O, and you form serpentine, which is called like this because it has the texture of a serpent skin. And the iron basically is released from the primary silicate. It oxidizes by reducing water. There's a transfer of electrons. And so you basically produce H2 as the iron precipitates into an iron oxide. And this reaction has later been observed in a lot of ophiolitic contexts, which are basically continental oceanic crust abducted at the surface of continents. And you can see here we have a lot of those all around the globe. It's not the only reaction that can produce geologic hydrogen, of course, even though it's the best known reaction. There's another oxidation reaction, which is sulfur oxidation. And you can see examples whether on the East African Rift, like Djibouti, where they have H2 in geothermal wells, or in Iceland, for instance. We do know there is sampotization in Iceland, but there's also H2S coming out. And if you oxidize this time not iron but sulfur, you can actually produce H2 and pyrite, or H2 and SO2. And you can see in Iceland they have, and this for 10-year-old paper, they've got up to 23% H2 coming out from their geothermal wells. So that's pretty interesting. And so the coupling geothermal exploitation and H2 exploration is actually pretty interesting because the wells are already there if you're in the right geological settings. Then, of course, there is radiolysis. You have probably heard about it as well. In uranium or thorium-rich granites, the water molecules get dissociated, and basically, as it breaks, H2 is released, and so is helium, helium-4 mostly, that accumulates in the continental crust. There are also coal-rich rocks. Most of you have worked on organic matter, certainly know this. As you get to deeper and deeper and higher temperature, you're going to crack organic matter up to a point where the only thing left are going to be bitumen and H2. Basically, it's a natural product of organic matter cracking. And a good example of that seems to be in the east of France basin in Lorraine. You may have heard of it in the media. They basically explored an old well in the Carboniferous levels of the basin, and they found out H2. And as they went deeper and deeper, the concentration of H2 increased. So they're continuing the exploration. It's now believed that France has a very, very big reservoir of H2 of many, many million tons, even though the quantification still remains to be done accurately. Now, of course, as I was saying, the main reaction, the one that everyone has been talking about, is serpentinization. But even though serpentinization deals with iron oxidation, it's not the only one. There are other rocks, Precambrian rocks, very old rocks in intracratonic areas, so that do produce H2. And that's interesting because then it would mean that the reservoir of H2, contrarily to petroleum reservoir, are actually into very, very old rocks, while most petroleum and gas reservoirs are actually into, well, Jurassic, Triassic, Cretaceous rocks. And so we do find H2 at the heart of continents, and that's what I'm going to talk about right now, starting with the mid-rift system. The mid-rift system of North America formed over a period of 30 million years in like over 1 billion years ago. It stretches over thousands of kilometers, and it's mostly kilometric scale accumulation of mafic and ultramafic rocks, which means it's very, very rich in iron. So it has a big iron oxidation potential. And you can see it here. This is a geological map of the mid-rift system. And those are the gravimetric anomalies. The anomalies are caused by the iron in the rocks. I could have shown you the same map with the magnetic anomalies, basically. In Kansas, hydrogen was discovered in the early 80s. Where they were drilling wells for water, and basically they found out that as the wells continued to be explored, IFP went back there in 2011, 2012, 2013, 2014. The level of hydrogen was actually varying. There were variations. The level of hydrogen went up to 92 mol%, and the EH of the water down to minus 248 millivolts. That's significant because it means that basically something is happening. If water is very reduced, it's because there's a reduced species that's basically bubbling through it. So it could be methane, and there's methane, or it can be H2. But what's also interesting is that the aquifer is actually passing through rocks that end up in the NEMA high, which is a geological trap that can actually, where gas can actually accumulate. And so you've got fluid rock interactions below the geological trap. If I take an exaggerated view of this area, this is the NEMA high, where basically the trap is supposed, the trap seems to be located. And there's a big fault, the Humboldt fault. What we believe is that hydrogen is being generated at depth here, and that there's a big accumulation, mostly because the basement is faulted and hydrogen comes back up. Now, of course, we have a reservoir, you also need a cap rock. And so we basically studied, thanks to rocks that had been sitting on the shelves of USGS for 20 years, the cores. And this is a small schematic that Valentine Cobondon did during her PhD. She just defended 6 months ago. Basically, you have at the very bottom of the core we obtained what appears to be iron-rich minerals, which are probably the H2 generating rocks. Above, it's very rich in carbonates, and those could very well be the reservoir rocks. And then, right at the top of the basement, above, you have black shells, which could very well be the cap rock. We developed a workflow to quantify this H2 because from the rocks, because again, not everyone is going to have access to wells, and as I was saying, geochemical exploration is a less expensive one. If you have cuttings of rocks or rocks in the area, you don't actually need to start drilling to see if there's potential or not. The first thing you do is look at the mineralogy and chemical composition of the rocks of the basement. And so basically, we did optical microscopy, focused ion beam. We went to the synchrotron to characterize the valency of iron in the rocks. Now that's very significant because remember, 2 moles of iron 3 yields 1 mole of H2. We did transmission electron microscopy, microprobe. We quantified the volume of each mineral in the rocks through microcore tomography. All that to try and quantify the H2 that had been generated in those rocks. And so I won't go into details, but this is those are calculations of the minimum and maximum H2 that can have been generated depending on the method used. So of course there is an order of magnitude difference. So we get up to 232 mole of H2 per ton of rock. And this is basically of the same order of magnitude that what has been quantified on the field according to literature, which are represented here. So this petrographic method, mineralogical method, is actually pretty interesting to get an idea of the potential of the rocks. Now, of course, there's a lot of techniques involved. And right now, there is a new technique that we are developing in partnership with Vinci Technology, based on the rock eval technology that has been used extensively for oil and gas to characterize source rocks in oil and gas basins. It's based on nearly the same processes, except that in addition to quantifying H2 from organic matter cracking, we added the H2 detector behind the rock eval, the hydrogen eval, sorry. We're also introducing water to generate fluid rock interactions and see how much H2 can be generated with temperature. And of course, then to be able to have something that will be significant for geological interpretations, we're doing batch reactors experiments at real environmental conditions to correlate the rock eval analysis and the natural environment generation conditions. But of course, this is not the only site where there is H2. And this is a map that where has been seen a lot of SCDs, what we come to know as subcircular depressions. It appears that in a lot of places where there is abundant vegetation, there are those what was used to be called fairy circles before, that can be up from 100 meters to 1 kilometer diameter. And we didn't really know what was the lithology, why did it generate there. And we believe we actually understood that. Every time we see those iron fairy circles, mostly it's because they are close to iron mines. This is South Africa. This is Australia. This is Namibia. And in Brazil, it's in Quadrilatero Ferifero. And the common point is that those iron mines are actually in banded iron formations, which, as some of you probably know, are, for most of them, very old Archean rocks, 3.5 to 1.8 billion years, even though there are exceptions with more recent banded iron formations in the Cretaceous, I believe. Banded iron formations, a small reminder, they formed in O2 poor early Earth atmosphere, mostly Archean and Neoproterozoic. They're chemical sediment, laminated. They have a high iron content, and the mineralogy is mainly chert, iron carbonates, magnetite, hematite, or pyrite. So they're rich in iron 2, but iron 3 as well. And we did experiments, basically. We tried to understand with various minerals of the mineral formation what was reacting at the lab scale. And we were very surprised when we tested magnetite, because for us, magnetite was the end product in serpentinization. It was supposed to be stable. And we tested it at, say, a lower temperature, 50 degrees, 80 degrees. And we found out that it was actually producing H2. We knew about the reaction that when magnetite reacts with O2, we form magamite, which is a polymorph of magnetite, but mostly actually where all the iron 2 has been replaced by iron 3. But we didn't know that we could actually produce magamite and generate H2 at the same time by reacting it with water in very reduced condition. And the amount of H2 were superior to every other minerals in the banded iron formations that we experimented on. And when you look at the beef, well, I mean, it does make sense. There is a lot of iron still in the banded iron formations. Of course, this is a course from the Hammersley province in Australia. When you go up at the very surface, it's oxidized, but as you get deeper, tens of meters, the iron gets more and more reduced. And so basically, if you have aquifers or deep water circulating, or even meteoric water that loses all its oxygen as it percolates down and reacts with banded iron formation, that has to be fractured, of course. Water has to circulate. That's a condition. Then you're going to oxidize the iron, and H2 is going to come up forward. This is probably why we do see so much H2 in banded iron formations or around banded iron formations in Australia. Now, we went up the rift. We were in Kansas and went all the way up to here in Minnesota, and we started looking at intrusions. And you know, we knew there had to be hydrogen because some paper had been published, and we saw stuff very similar to what we were seeing in Kansas that looked a lot like serpentinization in the volcanic intrusions. But there are also banded iron formations in Minnesota. And all of these, there's a lot of rocks that actually will not been looked at very much, where the cores are, a lot of them are still completely whole. And it does seem that hydrogen, there is oxidation, hydrogen can be produced along the iron range as well. So takeaway message for H2 source exploration. Well, firstly, use chemical data, EAGE or FO2 when it's available, from oil fluid data engineering database. And oil companies could very much have this data, even though they may not share it. Use satellite data. Look for subcircular depressions with low depth to diameter ratios. Use geological data. Look for magnetic and volumetric anomalies. And then, of course, use petrology data. You need to look for iron-rich rocks formations. And mostly, specifically, try to target iron mines and the iron-rich lithologies, such as this. all of these seem to be efficient proxies to discover, with cheap exploration methods, new H2 sources. Then, of course, sources are not enough. What about reservoirs? Well, at IFP, we were lucky enough to partner with Hydroma and Alain Princehofer, and we characterized the first reservoir of H2 in a pilot exploitation in Mali, in the village of Bourakédougou. And in those wells, you have up to 98 and 97% hydrogen. And the reservoirs, basically, and that's very interesting, they're very shallow. Like the first reservoir starts at 70 meters, and there's 6 superimposed reservoirs down to the basement at 1,500 meters. And they're mostly in either carbonates or sandstone. And the cap rocks are actually volcanic intrusions, dolerite, crystalline rocks. And in some places, there is fracturation, which seems to allow the H2 to flow in. So when talking about an H2 system, multiple characteristics should be considered. H2 generating rocks, migration pathways, true false. So it can move either as free gas or as dissolved gas. Tectonic traps, such as topographic highs like in the Nema in Kansas. Accumulation in reservoir rocks. It can be in a dynamic state where there's a constant recharge, or a steady state. It's hard to consider that, but maybe some of the hydrogen is actually fossil and has been produced a long time ago. In Mali, that does not seem to be the case because the reservoir seems to be recharging and the pressure keeps coming back up after it decreases. And then cap rocks, of course, you need cap rocks. Now we know this system exists, of course. We do have helium reservoirs on the planet. They are a reality, and both H2 and helium are small molecules. Helium is even smaller, difficult to trap, not very soluble in water. So what's the major difference? Why should there be a doubt about the existence of H2 reservoirs? Well, the main difference is reactivity. We know, we've done, this is from a paper that was published last August. We've tried reacting H2 with a microbial consortium that harbors hydrogenotrophic metabolisms at various temperatures with different substrates, different rocks, basically. And you can see that depending on the temperature, 25, 34, and 40 degrees, depending on the type of rocks, the H2 gets consumed actually pretty rapidly. This is a week. So trying to consider reservoirs forming over geological time is obviously difficult if you're in conditions where microbial activity is going to be very active. And of course, when you consume hydrogen, you can make methane, but you can make acetate as well, and you can make H2S. There are multiple products of hydrogen consumption. We went back to Minnesota to study those reactions on the field, and we basically used water wells all along Lake Superior. We sampled it, and we had gas accumulating. We were able to accumulate gas to analyze it in a water that was, when we were in the very, very mafic rocks, basically, but the water was itself very reduced and very basic. We went up to 11.5 pH, suggesting there were a lot of OH minus, so a lot of iron oxidation happening. Not a lot of H2 though. Huh? We went up to 500. The last analyses are a bit higher, 1000 ppms. Lots of methane, helium as well. Helium is there. But what's interesting is that when you look at what's in the water, you've got here formate, and on the x-axis acetate. Our samples are here, and all of these are in geological environments that are the most concentrated in acetate and formate in natural waters on the planet. All of these are mid-ocean ridges, ophiolites, and subduction zones. This is a mine in Canada, and this basically indicates that there is consumption of H2 in the subsurface, otherwise those values would not be so high. So the next big challenge actually is being able to model H2 behavior at the basin scale. And so this is an example from a study case in Colombia that was presented over a year ago. Our colleagues put a consensus of H2 at the bottom and try to image where the H2 would migrate depending on the temperature, the pressure. If it would remain dissolved, it would accumulate as free gas. What they still need to do, of course, is take into account the biological activity because that is something that is going to be very fast depending on the conditions. Doesn't mean it's going to be all the time everywhere, but it's something that it's one of the difficulties we're not facing at those time scales for oil and gas or natural gas like hydrocarbons. Voilà, I thank you very much for your time. And if you have any questions, I guess we'll discuss them after the next presentation. And of course, this work would not have been done without the help of many students and other colleagues. Thank you very much.
Thank you very much, Olivier, for your presentation, for dedicating these minutes to all of our audience. So thank you very much for joining us today. As you kindly said, the questions will be received at the end after Adriana's presentation. So please, as indicated in the chat, you are more than welcome to send all your questions through this channel. Now we'll go with the second presentation of the day with Adriana Traby. So while Adriana shares her screen, I'll introduce her today. So Adriana Traby is a geological engineer with a PhD in basin modeling. After 10 years of application of basin and petroleum systems modeling for the O1G exploration, Adriana joined IFPEN New Energies in 2017 and since then works with the application of basin modeling tools for the energy transition. Her work includes the identification of new development requirements, the proposal of applied research, and the application of recent developments for the CCS screening and the exploration for geothermal energy and fluids. She works in tight collaboration with other expert teams, coupling the basin modeling with structural restoration, geomechanics, and reactive transport modeling. She also teaches basin modeling courses at IFP School, NCGED, and Sorbonne University, and is involved in the supervision of internships, PhDs, and postdocs. Adriana, welcome to our webinar series, and thank you very much for accepting this invitation.
Hi, thank you. Thank you for this nice introduction. So I will continue the topic that Olivier introduced well, and with a very good slide for the transition. But I will start first with the lithium, and then I will come back to hydrogen and to talk about what to get from where he stopped the presentation. I just before starting the presentation, I would also like to say that this is really a group work, and there are several people involved. I'm not going to name them all because I'm going to forget someone, but I will like to acknowledge the work of Marie-Christine Cacas, which some of the work was it will be present in here, and it's the work that she presented in the last EAGE annual meeting. So this is the agenda of the presentation. I will start with a quick overview of basin modeling. I don't know if everyone is familiar with this tool. Just show how it works and how it is used for its main application, that is the petroleum system evaluation. And I will then talk about the lithium system particularities and modeling. And here we will focus on the geochemical challenges that we are facing wanting to model the lithium systems. And then I will jump into the natural hydrogen's particularities and modeling. And in here, since Olivier already talked a lot about the geochemical characterization, I will focus on the modeling of the migration, and I will explain why. And since this is an ongoing work, we have a lot of perspectives and further applications, and I will talk about some of them, and we can discuss with others later. So first of all, the 4D multiphysics basin modeling is a tool that allows to model the evolution of a sedimentary basin and the processes that takes place during the evolution of this basin. For example, during their sedimentation, you will have the compaction, so you have an impact on the porosity and the permeability that will affect the hydrogen hydrodynamic system, the pressures, can do the fluctuations. Once we are having the sedimentation and having the bureau increase, we will also have changes in the temperatures. We can consider boundary conditions, heating events, intrusions, and several events that can affect the temperatures. And with the temperature evolution, we can also assess the thermal maturity of source rocks. And so considering the kinetics of the source rocks, we can model the generation of the hydrocarbons and the migration of these hydrocarbons to in the basin. This image in here, this animation, is one example of one of the results of the basin modeling. There is the fluid saturation of the hydrocarbon saturation, and you can see that it starts from the deep source rocks and then it migrates, and you can see the fluid or the saturation getting higher and higher and accumulating somewhere in some places and then escaping in other places. And what is important in here, and that is an important point when we think about lithium or hydrogen, is that in here, when we do the basin modeling for the petroleum system modeling, we are usually working with a predefined source rock interval, in which we know that that is a source rock interval, that we have the kinetics and the characteristics of the source rock, and then the hydrocarbon is migrated there, and then it migrates. It can evolve the composition, it can be secondary cracking, but all the fluid rock interaction stops there. Then it's the rocks and the fluid that migrates according to hydrodynamics and the physical properties, but there is no more changes in the other layers of the model that are not source rocks. And since this is a tool that is really being developed for several years for the oil and gas, now that we are facing new challenges, that we have new objectives, it's normal to think of how we can use this tool that is quite powerful to other applications. For example, we are using basin modeling for exploration of CCS, of understanding the petrophysical, the characteristics of an area before injecting CO2 or using it for energy storage. But in this, what we do is that we take into account the geological history to better understand the present day properties. There is another very promising application of basin modeling that is for the exploration of new energies, of new resources, let's say, like lithium, helium, or hydrogen. But when we are dealing with this new exploration, with these new resources, we have different processes and different objects that we need to take into account, and that before some of them were really not taken into account, and others they were taken into account, but were not focused on them. For example, we had a lot of simplifications on the faults in our models, and we can see that both for the lithium, then for the helium, and for the hydrogen, this is really important features in the migration processes. And we also have a lot of new physical processes that we need to take into account. But can numerical basin modeling help? I'm certain that yes. How? This is something that we still, well, we have some answers, but I think there are a lot of ways that we still need to think of. So as I said, I will start with talking about the lithium system, and just with a small introduction about how we can find the lithium in accumulations, let's say. And for that, just we start with some quick properties of the lithiums. Well, we all know that it's really electroconductive, and this is why one of the reasons that we want to explore lithium. It's very reactive, so we never found it in its nature, in its pure form, and it's always associated with other minerals. One important particularity of the lithium is that it doesn't like to stay. It likes to stay in the liquid phase. So when we have the magmatic rocks, we usually find lithium in the most differentiated fractions of these rocks. And one thing that is important is that it's really soluble, and it doesn't like to stay. It's not compatible with silicates, and we usually only found it in traces and often as a substitute for magnesium. And so when we have the first deposits of lithium, we can have interactions with the water that can take the lithium from the rock. We can have the geothermal alteration, geothermal lixiviation, and we can have the lithium, and it will migrate with the water. And in some cases, it can accumulate in the brine phase. And this is what we are first trying to understand. What happens with the lithium that is present in these brines. And in order to accumulate in the brines, we have several factors that have been observed, that needs to have happened in order to enable the presence of this lithium enriched brines, either in salars or in paleosalars, or even in geothermal waters, or the waters, the brine associated with oil and gas, with brines in general. One of the things is that usually we have an arid climate, so we have evaporation, and since the lithium likes to stay in the water, it will concentrate while you have the evaporation. We usually have a closed system, so we won't have mixturing and some water with low lithium coming and mixing with it. We usually have geothermal activity because the lithium, the lixiviation of the lithium is facilitated in high temperatures, and you have the tectonic subsidence of the regions, rocks that has initially some interesting lithium contents that can be recovered by the waters, and sufficient time so that all this process can act and make the lithium be concentrated. We started working on the brine, in the lithium-rich brines in the Rhine Graben, since this is an area in France here where we know that we have lithium-rich brines, and that has been studied for several years now. And the first studies started really working with the composition of the water and trying to understand with the geothermometers, with hydrotopic correlation, trying to understand what was the source and when did this lithium arrived in the brines. Since then, there have been lately more studies focusing on the mineralogy of the rocks, trying to see if the observations that we do with the fluids can be correlated. And what we know for now from these bases, from these systems, is that this is a cross section on the Rhine Graben, and we know that we have two different, let's say, domains in the basin. We have the shallower sediments that have a water that the brine does not have a high salinity and has kind of low contents of lithium. And then in the lower parts, in the contacts between the sediments and the granites, we have these brines that are enriched in lithiums and with high salinity. So it's really a compartmented, a closed systems kind of. But we know also that all the geothermal anomalies that are seen in this area are related with convective systems. And so we have a lot of fluid circulations that are both on the faults and also on the fractures in this area. So we started working with using basin modeling, trying to understand these fluid circulations and the evolution of temperature at present, but also through time. And what we want to do is to link this, that can help us understand where are the areas where we can have the mobilization of lithium, and link this kind of first-case approach to reactive transport models in order to really simulate the enrichment of the lithium in the brines. Like, instead of having our source rocks with our kerogens and the synetics, we want to use to simulate these reactions, and then come back to the model and see how this brine will evolve in the model. Where would you go? We would be able to be focused in an area, we will be connected to other areas. But when we wanted to do this, we faced a problem that we also have in hydrogen when we want to focus on hydrogen, is that we do not have the data that we need for that. So we are still in the phase of understanding the processes, getting the data in order to be able to do all this coupling. And I'll just pass quickly to this. The problem is that not like I said, that in oil and gas we have one source rock, and then we everything all the generation what happens in the source rock. When we will be in this kind of system, in these mineral systems, we can have a first source rock, and then the water that gets the lithium or the minerals from the source rock, and then it precipitates again, and so an area that was not initially a source rock becomes a source rock. And so there are a lot of processes happening everywhere that needs to be taken into account. So this is a big challenge, and we are putting a lot of work, a lot of effort in this, but it's still a big effort that we need to go further in order to be able to really model these issues. I will skip that to this. This is the idea was the same thing that I said in the previous slide, and since I'm kind of running out of time, I will go to the next one. And here I just want to say that, as I said, the faults and fractures are really important when we are tackling these new subjects. And this is something that we did not use we're not used to handle well when we were doing the basic modeling for the oil and gas. And now we are really taking into account this and trying to work with some work that was already done for the oil and gas, but will be useful here to try to understand where we have fracturations, and so where we can have the fluid circulation, because the fluid circulations, like momentaneously, is with high source of energy, is really important in this mineral systems approach. And now switching to hydrogen, as I said, in the lithium, I was most talking about how we are trying to understand and how in the problematic that we are facing, wanting to model these new processes. And here, when I'm talking into hydrogen, I would just say that we have multiple sources that they are still poorly known, as Olivier already said, and so I will not focus on this part. I will more focus on the part that, as in his last slide, he said that we can work with some what-if hypothesis, and we can say, if we think that our hydrogen was generated in this area, how did it migrate it, and could it accumulate it in the basin? And for that, we have several points that we need to pay attention and that we need to take into account, and some differences between oil and gas is still. Some of them are regarding the migration. The first is that hydrogen will often migrate dissolved in the water, and so we need to take into account the solubility of the hydrogen and try to understand in which condition and where in the basin it will be dissolved and when it will be separated from to the water and will be in the vapor phase. We have a lot of diffusion, and we also have a lot of alteration, as Olivier said. We already implemented some alteration in the basic modeling, but unfortunately, the results that I'm going to show here does not take into account that yet, because it's really something really recent. And then for the accumulation, this is really something that it's a challenge. As you know, we need to have good source rock, good cap rocks, and we have to take into account all these alterations. And as Olivier said, for the Mali, here we are maybe facing or handling with more of dynamic accumulations than trying to really capture the volume in place and then working on it with the volume that are that. So we need to take into account the discharge rates and what's still coming from the source rocks. So I'll show you an example of an application that it was not really purpose for hydrogen, but was used for the hydrogen, in which we used some new functionalities that were developed not only for the hydrogen, but could be used for hydrogen. One is this solubility and to have the change between the water and the vapor phases. The alterations, and also the possibility of defining the areas in which we say, here we had the hydrogen generation. And since I said that the faults are really an important features in these systems, we are working with unstructured meshes. So here we work with a 2D modeling. Working in 3D is still a really big challenge, but we are working on trying to also do this modeling in 3D, because it's something that is really important in there. And so we have the fluid flow also taken into account inside of the faults. So this is one section that was used just for the application example. It's modified from the Perth Basin in Australia, and you have the permeabilities that were calculated for the model, for calculated from the basin model and then used it for the migration. One thing in here is that since we are working with the hydrogen system, we did something that we could never do in traditional basin modeling, is that we didn't take into account the past, the history. We're using this section, the present day geometry of this section, and imposing the hydrogen and the base of at some points. But the basin is fixed in sometimes. In the others, we did the restoration. And so we just to see the impact of these different factors and how different and how non-intuitive the results can be sometimes. We modeled 3 different scenarios. The first one is we have like a geological time scale. We have an injection in the points that are shown in here. This is injections, and it starts 50 million years ago, and we have a continuous injection rate of hydrogen. And in this scenario, the faults didn't exist. They were transparent. It's like they didn't exist. We have a second scenario in which we have the faults. There are 33 times more permeable than the rocks surrounding them. And we did the same parameters that we did in the first scenario regarding the injections and the timing. And then the last scenario, there is the one that I said that we didn't consider the past, but we only say what's happening in the very recent steps, and in which we used the same configuration of the permeability that's in this scenario 2, but we had a very high flux of hydrogen and everything working only in the last million year. So these are some results, and you can see the effects of these different scenarios. If we have the scenarios that is really being active for a long period of time, but we do not have the faults, everything is kind of dissipated and we don't have an important flux in the basin. This is what I'm showing here is the water velocity. It's not the hydrogen, but it's the water velocity. And when we consider the permeability of the faults, we can see that we can start having some permeability, some water flow that is taking place. But it's really when we push, when we have a really big impact, a really big influx of fluid from the base, from the faults, that we see an important impact on the hydrodynamic system. And we can see that here we have a really active system that is generated or created due to this influx of fluid in the faults. And so now, if we look at the hydrogen that is migrating in the model, we can see that with the first scenario, everything stays in the place where it was migrated, and it is kind of capped by a cap rock. When we have but we do not have big accumulations. Everything is kind of dissipated. When we have the permeable faults, we have the migration that goes into the top of the reservoir structures, and then we have some accumulation that are in the capped again by the seal, by a cap rock. And finally, in the very dynamic systems, what we have is that we have not very much, well, it's not been going on for a lot of time, but what we see is that even though we do not have the accumulations, we have some important accumulations at the end of the fault. So it's not really accumulations, but we have high saturations at this point, showing that we are having a flux of hydrogen and something that's staying there for a period of time. And now what is interesting is that if instead of looking at the saturation itself, we look at the recharge, and we can see that in this dynamic system, even though we do not have a lot of saturation, we have an important influx of hydrogen. And this could be interesting if we want to explore it, because since it is so reactive and can be alterated by bacteria or other processes, having a continuous influx is something that it is interesting to assess and to have if you want to explore the hydrogen. And in the presentation, we were talking about helium as well. So we are not in this example, we did not take into account the helium, but it could be something that we could also take into account since we have the properties and solubility of the helium, and we could put it into the model and see. It would be interesting to see how this everything can migrate together or not in the model. But if we want to take into account the helium, it is important to take into account the previous step and to do like we did in basic modeling, because the helium is not something that will accumulate very fast. It needs to take time to accumulate, and this is one of the papers who shows this, and that we can see that the helium productions when we look in the composition of a fluid, if we have a lot of more helium, if the concentration of helium is higher, it means that means that the generation, this gas has been generated for a longer time. Whereas in the hydrogen, it's something that can be quite fast. So just to conclude, we are running out of time. I'm sorry about that. Just want to say that for the multiphysics Bayesian modeling simulates the Bayesian evolution and the associated physical and chemical processes that takes place during evolution. And this methodology may also be very useful for the assessment of other natural resources. However, there are significant differences in the source, migration, and accumulation mechanisms that still require some understanding before being able to take them really into account in the models. But this is an ongoing work, and there are a lot of work going on in this topic. And I want to finish by saying that even though these two are still not yet, well, they are not yet predictive, we cannot really quantify or really use it as a really exploration tool. It's something that can already be very useful to test different scenarios, to test hypotheses, and to help us understand and de-risk these resources. So thank you very much for your attention. I'm sorry, I'm trying to come back.
No worries. Thank you very much, Adriana, for your presentation, also for your time and for sharing this research with all of our audience. I know that for the sake of time, we are now just like at the edge of our session, but we will just do a couple of questions from the audience before we end this session of today. So we have a first question for Olivier. So Yusuf Abubakar says, are organic carbon-rich high TOC rocks such as the Kimmeridge Clay Formation with TOC up to 60% considered as hydrogen-generating rocks? If yes, can the hydrogen from such rocks be substantial enough to be explored as a green energy resource? As a green energy source?
That's a good question. Honestly, I have no way of answering that right now because not every organic matter-rich rocks are going to produce hydrogen. Not every organic matter is going to produce hydrogen if you crack it. It needs to be tested. I'm not sure about it. It depends on the composition of the organic matter. Potentially, yes, but that's why we're trying to develop the hydrogen eval to test samples very easily and very rapidly. But I don't think the potential has been explored yet. The potential could be. I mean, you have to remember that in China, they do produce hydrogen mostly by cracking hydrocarbons. So, I mean, why not? But this is very different from, we don't really know, we don't believe, but honestly, we don't know, that's an open question, but we do not believe that this is the main source of geologic hydrogen. It mostly seems to be either radiolysis or iron-rich rocks, as most of the geologic hydrogen we found seems to be either at inophiolites or at the heart of continents in old cratonic rocks, where way before you have all those organic matter accumulations that are mostly from Cambrian era.
Thank you very much, Olivier. I hope Yusuf, this answered also your question. Now let's go with another one, in this case for Adriana, and this one was sent by Mohammed. Then the first question says, do lithium and hydrogen basing models require a significant larger scale than the traditional oil and gas basing models? Are plate tectonics also taken into account?
Well, we definitely need to add sometimes we need to add to the model. So this is something that we can do because we have water circulating through fractures, and this is something that we can take into account in the model and kind of having a larger scale, a bigger scale for the regarding the traditional oil and gas models. But for the plate tectonics, it's more like as boundary conditions. We will not have this in the models, at least this is not something that we are currently working on, but we can think of coupling this or having the results from one and being an input to the other.
Thank you, Adriana. Mohammed has an additional question. Is oil and gas data used as a calibration for the models? Example, PVT data and hydrogen content in hydrocarbons, lithium content in petroleum brines, etc.?
They can be. For now, we have not yet worked with the modeling of both systems, because if we want to calibrate with PVT data, we would have to also model the generation of hydrocarbon and the migration of the hydrocarbon. This is something that could be done. We haven't done it yet. But then, yes, we are calibrating the model in the same way that we did for the oil and gas models, and we are using the temperature, the vitrinite, every data that we can have, and we can use to calibrate the model.
Thank you, Adriana. We have another question. In this case, it is directed to you both. So maybe then you just let me know who would like to answer, or if both would like to answer. We don't have the name, but they say, I'm a PhD researcher working on geothermalism. My study area has very high water temperatures, reaching over 900 degrees Celsius, which leads to the formation of carbonate deposits. I would like to ask if you can recommend any laboratories where I could conduct modeling related to this topic, or if you know of any specific resources for such research. Thank you in advance for your guidance.
I don't have an answer right now, but maybe we can, if you can leave us contact.
You have easy resources online already with FreakC, which is free rock interactions code that is free to use. It's not very, there is a graphic interface if you do not like coding, and you can very easily model various reactions at varying temperatures. And for carbonates, the thermodynamic constants are actually pretty well known, so it will do it very easily. You also have the Geochemistry workbench from the University of Illinois. There is a free student version that you can download online. So I would encourage you to test both. And then, yeah, you can come back to us by email if you have more questions.
Yeah. We have our model also that does kind of the same thing, but it's not an open source. So you have to contact us, and then maybe can be some collaboration.
Thank you. Then we're going to end with one last question, in this case directed to Olivier before we end. So this one is now sent by Mohammed Nuraipur. He says, are ophiolitic environments more interesting than cratonic environments when considering geologic hydrogen exploitation?
Well, I mean, so ophiolitic environments, this is the same mineralogy and chemistry than the rocks on the oceanic crust. We do know the reactions pretty well. There are very high fluxes of H2 measured in certain parts of the planet on a lot of ophiolites. But they're not, those rocks are not porous, right? They're fractured, so water flows very easily. could there be an accumulation, and they're not as widespread as intracratonic areas. So the question is, you'd have to find maybe sedimentary cover over the ophiolites where H2 could accumulate, or could there be a reservoir in ophiolites? To be honest, there is a paper that was released about 6 months ago by a French team in Grenoble, Truch and collaborators, who studied the ophiolite in Albania, I believe, and they measure fluxes that, according to the calculations they made, cannot be explained by constant serpentinization rates, and so that leads them to deduce that there must be a hidden reservoir of hydrogen somewhere within the ophiolite. And so now the research is continuing, and they're searching for the reservoir. If we could find one, it would certainly change a lot. The question is, can we find accumulations? We don't know. So it's certainly interesting in terms of production, because we can stimulate the rocks. If we actually inject water at the right temperature, at the right depth, we could potentially produce very rapidly high fluxes of hydrogen. Then we'd have to catch it, basically. But can we find accumulations in ophiolites? We don't know yet. Hopefully we can, and that would make a very nice study.
Perfect, and thank you very much, Olivier and Adriana, for joining us today. For the sake of time, then we won't have so many more questions, but of course, if you have any more inquiries for our speakers, just share it with us, the communities at EAGE.org, and of course, we will extend them to the speakers and send you back their answers. Iseta Yusuf asks if we can share the presentations. Of course, this session has been recorded and it will be uploaded soon in the EAGE YouTube channel, so we can share this link with you all so that you can catch up with what was discussed today, and of course also share it with your colleagues interested in this topic. So thank you again, Adriana, Olivier, for joining us today. Thank you to all of our attendees for participating in this session. It was very nice to have you here, and we hope to count on your participation in our upcoming webinars from the EAGE-EAG Technical Community on Geochemistry. Thank you very much to you all. Have a good day.
Thank you.
Good to see you. Bye-bye. Have a good day.